Since the dawn of time, or more specifically 520 million years ago in the Alal Communis, dopamine has been controlling reward-based motivation and motor functions from the brain. Discovered by English scientists in 1907 and first synthesized by Swedish researchers in 1958, dopamine has since been confirmed to exist in almost all animals, except for the elusive sponge. Dopamine is classified as an amine and has the chemical formula C8H11NO2. This image shows the similarities between dopamine labeled DA in the human and monkey brains in a variety of regions. These were labeled using rabbit anti-rat secondary antibodies. Dopamine is produced in a few regions within the midbrain, the substantia nigra, the ventral tegmental area, and the hypothalamus. From there, it is distributed throughout the brain by a series of pathways: the nigrostriatal pathway, the mesolimbic pathway, and the mesocortical pathway. Before dopamine is distributed between neurons, it has to be synthesized. To do this, the amine phenylalanine combines with phenylalanine hydroxylase to create tyrosine. Tyrosine then combines with tyrosine hydroxylase to form L-dopa. Finally, L-dopa combines with dopa decarboxylase. After being synthesized, the dopamine, represented by the orange circles, enters the neuron through a specialized transporter protein. Inside the cell, it is packaged into vesicles, and it is stored until an action potential fires. For an action potential to fire, a series of signals are received at the axon terminals, both excitatory, or raising the charge of the cell membrane, and inhibitory, or lowering the charge of the membrane, which rests at -70 millivolts. Once the threshold potential of -55 millivolts is reached, voltage-gated sodium channels open, and positive sodium ions rush into the cell, depolarizing it. When 30 millivolts is reached, potassium voltage-gated channels open up, and the potassium ions flood out of the cell, repolarizing it. When an action potential fires, calcium will rush into the cell through its own transporters, which causes the vesicles to fuse with the membrane and release the dopamine through the now open voltage-gated ion channel. Through exocytosis, the dopamines leave the cell membrane and enter the synaptic cleft. From there, they either bind with a G protein-coupled receptor or are let in through a channel. More on the receptors in a minute. Finally, any remaining dopamines in the synaptic cleft are cleaned up through endocytosis. There are 5 receptors for dopamine, and they can be classified into 2 subtypes, D1-like and D2-like. D1-like receptors include the D1 and D5 receptors. Both of these are G protein-coupled receptors specifically connected to the GS-type protein. This protein creates an excitatory response when activated and leads to the release of cyclic AMP. D2-like receptors, which include D2, D3, and D4 receptors, have the opposite effect. They activate the GI and GO proteins, which create an inhibitory response, regulating the amount of cyclic AMP created. Dopamine is widely used in neuropharmacology, as deficiencies can lead to potentially severe neurological disorders like Parkinson's, psychosis, depression, and schizophrenia. However, dopamine has been widely studied since the mid-20th century, so many dopamine-focused treatments exist. Agonist dopamine medications include pramipexole and apomorphine, among many others, and antagonists include haloperidol and thioridazine. This is pretty much all the information that exists about dopamine, so I hope you learned something. Subscribe.